Okay, hello, welcome back. So in this video, this section, this module, we will be switching gears a little and we look at a different kind of formulation for dynamics. This one, the Hamiltonian equations or Hamiltonian mechanics, this is slightly different from the Newtonian mechanics and the Lagrangian mechanics that we had seen before. So in those domains, in those formulations, we were always dealing with position, derivative of position, and second derivative of position. So everything was based on a single coordinate, what we had up to a second derivative of those coordinates. In Newtonian mechanics, we were always working with 3D dimensions, the Lagrangian and generalized coordinates. We kind of extended the entire system in an n-dimensional space, and we had n second-order differential equations. In Hamiltonian, things are a little different in a sense that for every coordinate, I don't know, position x, consider a linear motion, instead of working with a second derivative of the variable, we break it into a two-dimensional space. So for every variable, every coordinate such as x will have a two-dimensional space, and we'll be working with two first-order derivatives. So we'll see how that goes. So to begin, let's start by a few reminders. So a few reminders. We know what is Lagrangian. We just saw it. Lagrangian is t minus v. And from there, Lagrange equations was d over dt of partial v, partial l, partial q dot I minus partial l, partial qi. Let's for now focus on the simplest case where we have independent q's and non-holonomic systems. So the most basic kind of formulation for Lagrange. So also maybe a reminder, maybe a new definition, depending on how you want to think about it. We had partial, well, let me do it this way. Partial t, partial q dot. We had seen this before. This is what we call pi, the generalized momentum. Generalized momentum. In a general case, actually, maybe let's call it a definition. Maybe in a Hamiltonian sense, we define pi, the generalized momentum, to be partial L, partial Q dot I. It is the same thing if you note that L is t minus v, and v usually doesn't have q dot in it. V is only a function of position. So these two are actually the same thing. But in a more general case, well, not general, a generalized case where the v, the potential function, may also include velocities. This is how we define the generalized momentum in a Hamiltonian formulation. And last thing, note that this is the same as what I had here. So in other words, what I can write my Lagrange equation, d over dt of this now being the momentum. So time derivative of momentum minus partial L partial qi equals 0, or we'll be using this much later. In fact, P dot is partial L partial QI. So this is another kind of, we already know this. Okay, that's that. These are the kind of the refreshers I wanted you to remember. Now let's begin. In Hamiltonian, we define Hamiltonian function. Let me write function to function. I don't like this. H. So my laptop is funny. I don't know if all surfaces do that. So there are regions on my screen that when I draw a line, I draw a straight line. It's only there. It is very noisy. You see? That tiny region is noisy. So anyways, H, we define it as functions of P, Q, and time. Let me write it a little bigger. So H of P, Q, and T is sum of all r equals 1 to n of Pi Q dot I minus the Lagrangian, which is Lagrangian, that's for now Q dot and T. So this is how we define Hamiltonian. It's a function. The function in the end has to be written in terms of P, the momentum, Q, positions, and possibly time. But this is the general way we can define it. And whenever we want to use it, we somehow have to convert these Q dots somehow in the function of Q's and P's to be able to work with the rest of the equation. But when we have this, then we can write something called Hamiltonian canonical equation. Hamilton's, not Hamiltonian. I say Hamilton's. Canonical equations are partial H, partial Pi equals Q dot I, and partial H, partial Qi equals minus P dot. Well, maybe I could write it this way. Minus this equals P dot. So these two are the Hamiltonian equations. And notice that for any generalized coordinate along whatever direction I have now two first order differential equations per coordinate. All right, so in general, I have 2n ODEs, first order ODEs. And remember, when we had before Lagrangian, we had n second order ODEs. Now we have 2n first order ODEs. First order. So here is the difference I was talking about. That before I had Q dot, and Q double dot, and we were always writing Q double dot, the second derivative, as a function of our Q dot and Q's. Here for every Q, every dimension, I have, or let me change the word. For every coordinate Q, I have now a two-dimensional kind of configuration, P and Q, that are associated with a single coordinate. Yeah. Let's look at an example. Maybe that would be more clear, or not super clear, but I think I'm gonna need this space. Let me write it a little further up. A super simple example just to show the concept. I have one mass M, just a spring K, and this is my generalized coordinates. And this example can show how you can use these equations in practice too. So T, the kinetic energy is simple, 1/2 mq dot squared. And the potential energy is 1/2 kq squared. So now that I know these, I can write my Lagrangian is 1/2 mq dot squared minus 1/2 kq squared. This is the Lagrangian. And from this definition, I can write my PI, generalized let's call it P, is partial L partial Q dot. That is going to be MQ dot. So we knew it. The momentum is mass times velocity. But now we derive it from a very general definition. So that's good. But maybe the tricky part is here. Remember this Hamiltonian. You need to write Hamiltonian, although this is the definition. Hamiltonian in general is only a function of P's and Q's. So I have to, wherever I see Q dot, I have to convert it to something in terms of P and Q. So let's do that. So I have Q dot here, and a Q dot will show up here. So I have to remove that. From this definition, P equals MQ dot. I know I can write Q dot as a function of P as P over M. So now that I have this Hamiltonian as a function of P, Q, and I don't have T here, but let's keep it. Let's do it. I don't have T. So my particular Hamiltonian in this example doesn't depend on time. Let me rewrite the definition. Well, I don't have summation either, so it's P Q dot minus L. Now let's substitute this. So P times Q dot, which is P over M, minus L. Lagrangian is 1/2 MQ dot squared, which is P over M squared, minus 1/2 KQ squared. And now my Hamiltonian is only a function of P and Q. If I clean up, I have P squared over M and minus 1/2 of P squared over M. So it is 1/2 P squared by M minus, and that minus becomes plus 1/2 KQ squared. And this is my Hamiltonian. And from here, I know my P dot is partial H, partial Q. Partial H, partial Q is, it's a negative, right? P dot, yes, P dot is a -1. So the only thing that has Q is that potential term. So minus KQ. That's my first equation. Second one, Q dot is partial H, partial P. The only one that has P is the first one, so it's P over M. Actually, it is exactly the same thing. Otherwise we would be screwed. We have two different derivatives for Q. So we retrieve the same definition through this. And now these two are describing the motion, these two equations describing the motion of just a single mass moving left and right. To be able to fully solve the motion of the mass, we have to simultaneously integrate P and Q. So a few things to note. First thing, so let me rewrite this Hamiltonian. Let's go back to the first definition. P is MQ dot. So let's if I write this P as MQ dot. So I'm going a little back and forth, but that's the reason. So it is going to be 1/2 M Q dot squared plus 1/2 K Q squared. So 1/2 velocity squared plus the potential energy of the spring. This is actually the total energy of the system. And maybe with nicer color. So Hamiltonian is always equal to the total energy of the system for, oh, this one gives me trouble. This what? Celeronomic systems. These celeronomic systems are those systems where t time does not appear in equations. This is equations explicitly. So essentially in kind of good behaving mechanical systems that we often work with, those for instance that don't have internal drivers, like I don't know, a motor or a hydraulic linear actuator or things like that, that enforces some change with time within the system. If we ignore those conditions, Hamiltonian is the energy of the system. So we can possibly calculate it in simpler ways and write it in terms of P's and Q's and write the equations of motion as so. So that is that. Again, noting that instead of instead of 1/2 order equation of motion, now we have 2 first order equations of motion. And something I want to emphasize here, we are really not getting away with the notion of acceleration. So P, momentum, the derivative of momentum has in it this notion of change of velocity. So essentially we still have that. We still didn't dodge that concept of acceleration, but now written it as a form of these coupled first order differential equations. What else? yeah, you can see here this P dot is actually equal to the force. So it is in some sense, well, it is Newton's second law, this second equation. And the first one is just the definition in our simple case, just the definition of momentum. All right, so let me see if I'm missing anything. No. Okay, the last thing, maybe it is obvious, maybe not, but where do these equations, we pull this Hamiltonian definition out of our hat, and then we wrote these Hamilton's equation just out of the blue. Maybe it's not a proof, but I can show you roughly where they come from. So Hamiltonian is sum of P Q dot I I1 to N minus Lagrangian. Let's keep it at Q dot and T. This is N. So partial H, partial Q I. Which one do I have first? Pi. Partial Pi. So if we leave Lagrangian as is, as a function of Q dot, well, this is not a proof, but this is a very sloppy demonstration. So this one Lagrangian doesn't have momentum in it. The only momentum is PR, so, and partial derivative with respect to that particular I is our Q dot I. That's the only term that has Pi in it. Partial H, partial Qi. The first one doesn't have Q, and only I have the Lagrangian, so it is minus partial L, partial Qi. And we saw up here that partial L, partial Qi is P dot, so minus P dot I. You can kind of, if at any time you forgot, you can easily derive these from the definition of Hamiltonian. Okay, that is all I have for now. Maybe in another video I talk about a little bit of other stuff in relation to Hamiltonian, and we can wrap this up. So until then, I'll see you then.